I'm Chen Guanglu from Ericsson. I'm here in VideoEuCNC 2016, and we are here to demo our front haul compression. This work is part of a 5G Crosshaul project, and we also collaborated with UFPA from Brazil and ATH from Sweden. And this work is mainly about improve the current front haul interface. This interface now have a big challenge in too high capacity. So if you want to support centralized or cloud run architecture, then this is too much capacity. You need to pay a lot of cost. And the main problem is high capacity. We want to reduce the capacity by compression. So because we have observed in the front haul, current front haul link, there's a lot of redundancy in the samples. So basically, we try to improve the CPRI, the time domain front haul used in CPRI. So the IQ sample compression. And we have derived, first thing we have derived is it's a bound, basically. We have derived a lower bitrate bound for front haul. Then we know it is possible and achievable to achieve more than 5 times compression. But there's a trade-off between the air interface performance and the front haul compression ratio, for example. The more you compress, and the less air interface performance you will get. But the trade-off, but it is enough to support very high performance for the air interface, even with 5 times compression. And in this demo, we implemented a linear predictive coding-based approach to get closer, very close performance to the bound. So basically, the idea is like because of the redundancy, you have so there are correlations between the samples, and we use the previous samples to predict the current samples. And then we take the difference between the current sample and the predicted samples, and then the error sample between them will be much smaller than the original samples. Then that means you can use fewer bits to quantize with the same accuracy in the signal. So then, in order to further increase the compression, we use lossless compression scheme, like Huffman coding, to compress it further. Then on the other side of the front haul link, for example, the BBU or the RU, then we will decompress the samples to recover totally the original sample, the sample bit width, for example, the number of bits. In the end, then we can achieve, here we show a demo, we implemented in the FPGA. So we show 4.8 times compression. With the implementation, the current implementation, we can achieve 4.4% EVM, and that is enough to support 64 QAM. That means with 75 megabit per second per 20 megahertz carrier, then you only need 190 megabit per second instead of 922 megabit per second in the original CPRI. So this significantly increased the efficiency of the front haul. And if you want to achieve, support 256, the maximum capacity of the interface for 100 megabit per second traffic throughput, then you better to do then we can achieve 4 times compression. That means we need around 230 megabit per second to transport the front haul. Then you can achieve 2.2% EVM we show here in this demo. So then we show for 4 to 5 times the compression ratio, you can get the very good performance for interface. Then you can transport, the network can transport more carriers, or this curve show actually it's possible to adapt the front haul bit rate with the air interface performance and the front haul link quality. For example, if you have congested link If later you want to transport the front haul over Ethernet with packetized interface, then you have to, then if the network gets congested, then you can move to a more compression point, then you lower the bit rate, then you still get the cell alive, you don't get the cell down. So that's a very good feature.
Hello, my name is Jakub Kocur and I'm working for Core Network Dynamics in Berlin. Here at 5G Crosshaul project booth at VideoEuCNC conference in Athens, we are showing a prototype implementation of a C-RAN with a new functional split between the ROC and PDCP layers. We are working with cooperation with Fraunhofer HHI, which provides the wireless optical link for the front haul solution. As a part of our demonstration, we are showing a full LTE attachment using our emulation of an LTE user equipment. From the graphical interface, we can trigger LTE attachments, which will connect us first to the RU and BBU and then to the core network. All of this enables us to establish a default bearer to have a connection with the core network and the PDN network connected to it. We can also check the connectivity, and as I mentioned before, the front haul link is done over wireless optical link, which means whenever a connection is interrupted, the connectivity is dropped. And as soon as it's resumed, the connectivity is back up. The biggest advantage of the proposed solution is the reduction of the requirements for the front haul, which enables us to use a variety of different technologies like wireless optical link or millimeter wave that we are going to integrate later in the project. The other advantages that are coming from the proposed functional split are also the centralization of the upper functionality of LTE protocol layers like PDCP, RRC, bringing also some advantages, and also higher flexibility in deploying the BBU elements, which can be fully virtualized and deployed together with a virtual EPC as another VNF. The further steps for the project are including the integration with full LTE physical layer, as well as integration with millimeter wave mesh network as a front haul and back haul solution.
Hello, my name is Peter Farkas. I'm from Fraunhofer Heinrich Hertz Institute from Berlin, Germany, and I'm demonstrating the optical wireless point-to-point communication. It's an LED-based device, and it has several advantages, such as a wider light beam, which is easier to catch at the receiver side. So it is in the deployment or setting it up, it's much easier to track the light and to align the two devices. And apart from that, is also no tracking needed. So an LED-based light communication allows, in this case, 500 megabits per second over 100 meters, or it's also possible over 200 meters to reach 250 megabits per second. The use cases are to have point-to-point communications for inter-building communication, for Wi-Fi access point connection, or for LTE small cell connection. And in the 5G Crosshaul project, we are developing it further to reach beyond 1 gigabit a second. Our goal is to go to 10 gigabit per second over 100 or more than 100 meters. And it will be in future a good alternative for backhaul, short-range backhaul connections between 50 and 100 meters. So this demo is set up with a device with actually with a red LED. So, but best performance is with infrared light. But only to show it, we have it in a visible light range, and there's connected to a live IP camera, where we can see the picture on the other side, so it's a live video feed. And even if you block the connection, the picture is frozen and it will build up in several seconds and just continue the transmission.
Hi, my name is Shang. I'm from Yichi, Taiwan. In Taiwan, we have a high-speed rail, and we have been working with the high-speed rail company for years to bring the broadband communication to train passengers. For years, we work on many things. For example, we work out radio fiber systems, and we developed it in the tunnels to overcome the poor signal coverage in tunnels. Still, there are many challenges we need to overcome for high-speed rail communications. For example, the frequent handover due to the very high speed of the train, and a smooth handover is very critical for high-speed rail communications. And we also want to share the infrastructure and the network among many operators so that they can share the same infrastructure using the technology so that they don't have to install their infrastructure, everyone. So in this project, Crosshaul project, we want to integrate the architecture and the technology in this project, and we want to contribute our innovations to this project to solve the problems we face in high-speed rail communications. So in this project, we will develop mobility management applications, which is a handover mechanism to reduce the handover time. We try to introduce some base station process or core network process in the Crosshaul, and without modifying the handover process, but we can reduce the handover time. Also, we want to develop a multi-tenancy mechanism so that we can partition the physical network into many virtual networks and for many operators and make it efficient and dynamic. Also, for the RF, we want to integrate the controller developed in this project to achieve network management as well as interference suppression. So our ultimate goal is that the train passengers can have the same experience even when they are moving very fast.